It's on now.
Yeah, thank you. Hello, class. Welcome again to today's lecture. And we're starting with thermodynamic process. It's a continuation from where we stopped the other day. And we looked at those three thermodynamic processes. We looked at reversible and irreversible processes, processes at constant quantity, and then cyclic processes. Like I introduced these reversible and irreversible processes to you earlier. If the properties of a system change in time, at least one thermodynamic quantity changes. We say that a certain thermodynamic process takes place in the system. So the term process relates to a very broad range of most varied processes, from simple physical change like heating to various chemical reactions up to complex multi-stage processes. And so these processes can be classified according to several criteria, like I mentioned earlier to you. One, we have reversible and irreversible processes. We have processes at constant quantity. We have cyclic processes. So the different processes are classified into these three sets of processes. So looking at reversible and irreversible processes, let's see how I'll explain to you and you'll be able to understand it easily. So the course of any process depends on the conditions under which the given system changes. So if we arrange conditions in such a way that the system is nearly at equilibrium in every moment, and that also consequently the direction of the process may be reversed by even a very slight change of the initial conditions, that is when the system is at nearly equilibrium. So a slight change can cause a reverse, and so you can either go to the front or go back. Of nearly equilibrium states of a system. So, however, there are processes in the real world are mostly such that they are not equilibrium, and at least at the beginning. So these processes that are non-equilibrium processes are otherwise called irreversible processes. Irreversible, that's they go on one direction. They go straight on one direction and they cannot be reversed. Like I explained to you the other day, that such reactions, we see the arrow pointing straight to one side, unlike reversible or equilibrium processes that you have arrow to back, the other half arrow to the front. That means it can be shifted at any moment. So, but irreversible is just so, and an equilibrium process is thus actually a limiting case of a non-equilibrium process going on at an infinitesimal velocity. That's at every little moment. So let's look at an example here. Infinitely slow heating. You heat a system slowly, or you compress it slowly. That may serve as an example of equilibrium process, which cannot be carried out in practice. Equilibrium process is difficult to carry out in practice. So in contrast to that, we have another example of water boiling at a temperature of, say, 100 degrees centigrade and pressure of 101,325 Pascal. This is an example of an equilibrium process which may take place in practice. This particular one, of boiling water at a certain temperature and pressure, it's an equilibrium process that can take place in practice. So in this case, if we lower the temperature slightly, the direction of the process will be reversed and boiling will be replaced by water vapor condensation. So this one is an example of equilibrium process. You let it boil and you can reduce the temperature and then it goes back. So that is an example of an equilibrium process. So now going on to processes at constant quantity. I'm in a class, please. So processes at constant quantity. I mentioned to you 3 types of processes. All the different processes, whether it's simple, multi-stage processes, they can be classed into 3 sets. I've just talked to you about reversible and irreversible. And then this is another one, processes at constant quantity. And then after this, I'll talk to you about cyclic processes. So the processes at constant quantity now. In most investigated processes, one or more thermodynamic quantities are maintained constant during the process. So these processes are mostly termed using the prefix iso or IS-something, denoting using the symbol X, with X indicating the given constant quantity. So as you can see in this slide, you see the following processes are encountered most often. You can see the slide that I have now. You see the name of the process, you see the constant quantity and the symbol that is used. So if you have iso, like I've told you, we use prefix. Here we have isothermal, which means the process is taking place at constant temperature, and you denote, the symbol is capital T. If it is taking place at constant pressure, you call the process isobaric, and then the symbol is P. If the process is taking place at constant volume, you call that process isochoric, and the the symbol for that is V, capital V. If it's taking place at constant heat, then that is adiabatic. And the symbol is just small letter AD. If it's taking place at constant entropy, like I've told you, entropy is the degree of disorderliness of a system. So if the process is taking place at constant entropy, then you call it isentropic. The symbol is capital S. If it is taking place at constant, symbol is capital H. If it is at constant heat capacity, you call it polytropic, and the symbol is capital C. So we have several processes that can take place at constant thermodynamic property. So let's see an example here. In the initial stage, this is an example I want to show you. Initial state of a system, the system of a constant volume. Note all these properties. At a constant volume, has a temperature of 300 Kelvin and a pressure of 100 kilopascals. A certain process takes place in the system, and in the final state, the system temperature changes to 320 Kelvin, and its pressure is 150 kilopascals. So now, does the process take place under a constant thermodynamic quantity? So if you say yes, so what thermodynamic quantity? The initial and final temperatures of the system are different. You can see the initial temperature is 300 Kelvin and the final one is 320 Kelvin. So you can see definitely the temperature has changed. And so that process did not take place at a constant temperature. So the process cannot be isothermal. And then let's look at the pressure. Both initial pressure and the final pressure are identical. Being identical, that is, you can't see any change. It could be isobaric, or it might not be. Why? Because in the process, during the system changes, you cannot tell. Maybe at a particular stage, there was a pressure change before it finally got back to the same pressure that it took, that it's an isobaric process. And so in this case, it can be and it might not be. This specification here does not allow us to find out whether pressure changes in any way in the course of the process. So that's why we cannot really say it's isobaric or not. Now, however, the process is definitely isochoric one. It's definitely isochoric. You can see in the beginning, in the first sentence there, that it said that the system of a constant volume. When the process is taking place in a system at a constant volume, then that is isochoric. So this process definitely is an isochoric one because the system has a constant unchanging volume. I believe you can understand now what we mean by process taking place at constant thermodynamic quantity. Now let's get to the cyclic one. We go to the cyclic process. What is a cyclic process? I believe you have an idea. Something happening over and over and over again. So a cyclic process is such at which the final state of the system is identical with the initial state. The final state of the system is identical with its initial state. In a cyclic process, changes of dynamic quantities are zero. You want to subtract the initial from the final, or you cannot find anything because it has gone back to the initial state. Everything is the same, initial and final. So it will be zero. So, and note that heat and work are not thermodynamic quantities. Therefore, they are not zero during cyclic process. So it's only thermodynamic quantities we are talking of. It will be zero during cyclic process. So let's look at an example here of a cyclic process. Let's say we have a system to be a cube of ice. That's what we're studying, a cube of ice with a mass of 1 gram. And the initial state to be a temperature of -10 degrees centigrade and a pressure of 100 kilopascal. I hope you're noting all this. Mass of 1 gram. Initial state of the temperature is -10 degrees centigrade and a pressure of 100 kilopascals. We're talking of ice. The sequence of processes taking place in the system was as followed. The cube was heated. I want to take you through the process now to see how it is cyclic. The cube was heated to 0 degrees centigrade. At that stage, it melted. From being a cube, it melted. So the liquid water now, that cube melted to, was electrolyzed at this temperature, 0 degrees centigrade. So when it was electrolyzed, it produced a mixture of oxygen and hydrogen. And this now is a gases, and it expanded to 200 pascals. Then the water vapor that is resulting from this reaction had a temperature of 500 degrees centigrade. You have seen that the temperature is rising from 0 now to 500 degrees centigrade at the end of the reaction. And then the system now was cooled again, cooled to -10 degrees centigrade and compressed back to 100 kilopascals. So in the course of compression, desublimation took place, that is slowing. Now from that gas went back to block ice. And the system returned to its initial thermodynamic state, which is a solid. So this is a cyclic process that took place from -10 degrees centigrade temperature and pressure of 10 kilopascal. And a lot of things happened in between and finally ended up again at -10 degrees centigrade and 100 kilopascal. That's a cyclic process. So now, let's look at what we call extensive and intensive properties, thermodynamic properties. So any characteristic of a system in equilibrium is called a property. Any characteristic of a system in equilibrium is called a property. So we have different types of properties. We have extensive properties and we have intensive properties. I will give you some examples of extensive properties. Examples of extensive properties are volume, mass, and total energy. Why are they extensive properties? Extensive properties vary directly with the size of the system. They vary with the size of the system. So volume has something to do with the size. Mass has something to do with the size. Total energy also has to do with the size. So this is why it is this example extensive properties. But intensive properties are those ones that are independent of the size of the system. For instance, temperature. The size of a system, the temperature doesn't depend on the size of a system. A small size of thing can be hotter than even the bigger size of matter, of anything. So temperature doesn't depend on size. Pressure also doesn't depend on size. Color doesn't depend on size. A big thing can have a light color. A small article can have an intense color. So all those characteristics of a system in equilibrium, which are called property, all those, I've told you intensive and extensive properties. So those examples I've given to you, now you can see what property is extensive, which one is intensive. But now, as I've told you that extensive property varies directly with size. I mentioned volume and mass and total energy. I want you to note something, that any extensive property per unit mass is no longer extensive property. It has changed to an intensive property. Extensive property per unit mass has changed to intensive property. For instance, you have your specific volume, small letter v, which is volume over mass. Which is mass over volume. Those ones, they are intensive properties because of the mass that is involved. Okay? So you can have these questions in your exam. And so you should please carefully look at them so you don't get confused in exam hall. Check carefully and see which ones are intensive, which ones are extensive. Definitely, I want to tell you, this will come out in exam. So go and pay attention to it. Now, let's look at spontaneous processes. So spontaneous reactions, or a spontaneous reaction, is a reaction that occurs under specific conditions. I will explain as we go on. Whereas non-spontaneous reactions do not occur under specific conditions. So, for instance, you have a waterfall running downhill. That's an example of spontaneous process. I will explain more. A lump of sugar dissolved in a cup of coffee. Just put coffee in a cup of coffee, sorry. Just put coffee in a cup and then put sugar there. You don't need to do anything for that sugar to dissolve there. On its own, it will dissolve. Just like water will just run on its own down the hill. You don't need to do anything for it to run down the hill. At 1 atmosphere, water will freeze below 0 degrees centigrade. And then ice also will melt above 0 degrees centigrade. You don't need to do anything more. Heat flows from hotter objects to colder objects. So, for instance, if you boil water, the water is boiling very well in a kettle. Now put off the fire, switch off your gas, and then leave the water there. You know very well that the kettle of the hot water is far hotter than the surrounding. You leave it there. After a while, the heat will flow easily out of that kettle into the environment on its own, into the surrounding on its own. You don't have to colder side. You only need to do something to bring something from colder to the hotter, which is not a normal situation. So all these are examples of spontaneous processes. Iron that is exposed to oxygen and water will definitely form rust. You don't need to do anything about that. So you can see on your slide here, spontaneous process. When you're sliding down a hill, it's a spontaneous process. You just slide down without having to do anything. So what a spontaneous process is that process that happens without you applying any force or having to do anything about it. You need to apply force for some reactions or some processes to happen. But that one that will happen on its own, just on its own, without you applying any external force. So let's look at spontaneous processes and entropy. I believe you remember what I called entropy, how I define entropy for you. So disorderliness, measure of disorderliness, that is entropy. A process will occur, but it doesn't give us information about how long it will take for that process to occur. So the amount of time that is required for the process to occur, thermodynamics doesn't give us that information. But it tells us whether the process will occur or not. And like I've mentioned to you before, a spontaneous process is the one that occurs without outside intervention, without any external force, without any outside intervention. That's a spontaneous process. So now we're moving to our lecture 6. I want to look at the first law of thermodynamics. Outline here. We will see the forms of energy, energy conservation, concept of work, pressure volume diagrams, concept of internal energy, Joule's law, thermal capacities or specific heats, concept of enthalpy, various forms of the first law of thermodynamics, we will see them, and then we talked about the types of processes already. So, forms of energy. Earlier, in our previous lecture, I mentioned to you kinetic and potential energy. Kinetic energy as energy in motion, and potential as positioned energy. So let's look at the different forms, all different forms of energy that we have. We have internal energy, which I told you is a sum of all the different forms of energy. We have kinetic energy, energy in motion. We have potential, position. We have mechanical energy. We have heat energy. We have chemical energy, and we have electrical energy. So, let's look at energy conservation. This is to do with the first law of thermodynamics, energy conservation. And the outline I gave to you in this particular lecture, I mentioned that we will look at how we can state the first law of thermodynamics in different ways. So this is what I want to show you now. One, first law of thermodynamics states that total energy is conserved for any thermodynamic system. Total energy is conserved for any thermodynamic system. That is one way you can state the first law of thermodynamics. Another way you can state is that energy cannot be created nor destroyed. Energy cannot be created nor destroyed. This one, you will see it, I think the lecturer that will take over from me will handle that aspect. But I think I'll still be able to show you, I'll still show you some part of it before it gets to her own lecture side. So the second one, I say energy cannot be created nor destroyed in the course of any reaction. The third definition is that energy can only change from one form to another. Energy can only change from one form to another. So if you have an understanding of energy as it is, then it will be easy for you to have full understanding if you're in a given topic. Let me look at this aspect that I say energy cannot be created nor destroyed, but it can be changed from one form to another. For instance, I want to give you a practical example. Let's say you have something like amala and ewedu soup. You want to eat amala. Maybe it's when it was raining heavily and it's so cold, and then your mom prepared amala and ewedu, and you want to eat. And that the energy in that amala is chemical energy, is what you have in that your amala. And now, if the chemical energy in that amala is, say, I'm just giving any value, let's say it is 100. Remember, the first law of thermodynamics tells you energy cannot be created nor destroyed. Tells you energy can only be changed from one form to another. Now you have your chemical energy in your amala and you're ready to eat it. So when you eat that amala, that chemical energy broken into two forms of energy in your body, and you will feel it. It will be broken into heat energy and kinetic energy. To be broken into heat energy and kinetic energy. And so you'll see that maybe if you were weak before, you have strength to do work. You'll be stronger. That's the kinetic energy you got there. And the other one, the heat energy, you will feel heated up a bit. You're no longer cold after eating that food. In short, if it wasn't cold, you ate it, you will start sweating. So you now have the heat energy, your chemical energy change or broken down to heat energy and kinetic energy. So like I mentioned, let's say the chemical energy definitely have now will be what you have from the heat energy and the kinetic will sum up to 100. You will not have anything less than 100 when you sum the two. So that is an explanation that energy cannot be created nor destroyed, but it can be changed from one form to the other. By the time you sum it up, it will still give you what you started with. I think you'll be able to understand that. So now, energy is constant. So you can now, well, let's start doing some relationship now. We'll end up with some calculations. Energy with the symbol capital E is equal to is constant. So now you have your different forms of energy. You have your internal energy, your kinetic energy, potential energy, mechanical energy, heat energy, chemical energy, electrical energy. All of them is equal to constant. So let's start from there. So E is equal to constant. Work. Let's look at work. We'll still use that energy later on. Concept of work. Work is a mechanical form of energy. Work is a mechanical form of energy. Let's define work in a relationship form. Work is equal to force times distance. Work is equal to force times distance. For work, dW, a little change in work, is equal to F, that is force, times distance, delta X. Why do we use delta X for distance? X, you have points there where you start from, initial point, and you move at a distance to another point. So the last final point, subtracting from the initial point, gives you that delta X. That's the distance. So you have work is equal to force times distance. And you see in that relationship, dW is equal to F times delta X. Okay. And then, if you recall the definition of pressure, that pressure is the same thing as force over area, force over area. So now, from that, using pressure now, relating pressure with force and area. So what will your force be? Force becomes pressure times area. Pressure times area. Remember, I said dW is force times distance. That is, work is equal to force times distance. So when you now replace force with pressure times area, in place you have F, you now put P times delta X squared. You know, distance is X, area is X raised to power 2. Volume is X raised to power 3. If you can remember your distance in meter, your area in meter square, and your volume in meter cube. Okay? So now, where you had F, you replace F with P, that's pressure times delta S squared. And now that is why you now have the final, when you substitute this into your initial equation there, dW is equal to F times delta X, you now have dW is equal to P dV. PV, that is pressure times area, that is your force. You have substituted pressure times area in the place of force. And you remember that you already have one distance there. So you already have, so that you now have your X squared, delta X squared times delta X, and that gives you delta X3, delta X cubed. That delta X cubed is your delta V. The X cubed is your volume. So when you replace it there, that is how you now can define work as dW is equal to P dV. Okay, let's go on. Now we're going to apply it. So we're still now looking at the concept of work. We're going to apply what I just told you now. Changes in volume cause work. Work is performed when air expands. Let's say you have a balloon. You have a balloon. When it is down here at you have a balloon. So when the balloon is down here at the surface, it just stays, it's not expanded. But as you move it up, it will be expanding. As you move it up, it will be expanding. Why? Why is it expanding? Because the higher you go, the lower the pressure. The pressure keeps decreasing with height. And so what happens? Then the system starts doing work, the environment. The system starts performing the environment. The balloon is expanding and pushing the environment, as you can see here. So it can keep on going. As the higher it goes, the more it expands, because the less pressure that is built on the balloon. And so now you have dW. In this case, the work that is done is more than, is higher, is greater than 0. Work done is greater than 0. So you have work done greater than 0, is positive, as your balloon is expanding, as it's going up. And the reverse is the case when it is coming down. The more it comes down, the more pressure acts on the balloon, because the pressure down is higher than the pressure up. And so the balloon will be compressed. In that case, the environment is doing work on the balloon. And so it will be compressed. And in that case, dW will be less than 0. It will be a negative, to give you a negative work. When the balloon is coming down, it's contracting because of the pressure that is on it. And so you have dW as negative, that is less than 0. So pressure volume diagram is still just explaining that, what I just told you. So you have dW is P dV. And when you do, this is your integration, and you do, so whether the volume, the area that you see here, that is shaded here, is the work done under the initial I here and the final F there in that curve. So first law of thermodynamics, we're still there. Let's look at internal energy. Internal energy is kinetic energy plus potential energy of the molecules in the system, in the particular system we're studying. And so internal energy depends only on the current state of the system, as the pressure, the volume, and the temperature. Current, not on the past state of the system. And internal energy also does not depend on how the state changes. It only depends on the current system, on the current state of the system. So changes are the result of external forcing on the system, so in form of work and heat. I told you in the previous lecture that you can relate energy and work and heat. So internal energy delta E is equal to work plus heat. du is minus dW plus dQ. Why minus? When work is done on the environment by the system, you have minus sign. When work is done on the environment by the system, it gives you minus. So you can see here, work done on environment. But when environment does work on the system, that is when you have positive work. So in this case, we have the internal energy is work done on the environment plus the heat of the environment. So you have du is minus dW plus dQ. And remember that dW is equal to PdV, like I've shown you previously in the past slide. dW is PdV, so you now see that du is minus PdV with PdV. So now Joule's law. We will look at this, and we're having two valves, we're having two balloons. One has air, the other one is vacuum, and you have a connection that's connecting the balloons. You have a valve that you can close or open. And these balloons are in an insulated system. So please mute yourself. Who is there? Mute yourself. So let's go on. Before we complete this lecture, you will be able to see more of this. We're going to explain this as we go on. So you see now, when you open that valve, when you open the valve, the air is on its own flowing into the other one that was a vacuum when you open the valve. And so air expanded to fill the container. There's a change in volume, but no external work was done. The air expanded into a vacuum within the system. No external work was done. No heat was added or subtracted. This system, like you can see, is thermally insulated system. No work was done, no pressure, nothing. It's expanded. And so in this case, dW that we have, that is minus PdV plus dQ, will become 0 because there was no work done on the system. There's no pressure change. There is no heat added. And so all those, the PdV and the Q are canceled, so du becomes 0. So now,
No, don't worry.
Who is making that noise? Who is making that noise? And then don't make noise, please. If you're not muted, mute yourself. Okay, so internal energy is only a function of temperature. So that's why we have this relationship that U is U T. Let's look at these types of processes. I mentioned to you that we have processes at constant volume, constant thermodynamic functions. So we have here constant thermodynamic quantity. We have processes at constant thermodynamic quantities. So like the isobaric I mentioned to you before. So if we now make use of the equation we have, that delta U is Q plus W. Internal energy changing in internal energy is work plus heat. So in this case, remember that work is PdV, and then when there is no pressure change, then you end up with the internal energy being isobaric process. There's no change in pressure. When there is no change in volume, you know, so you now have your delta U as Q when there is no change in volume. We're making use of that relationship between the internal energy, heat, and work. That is what we're using in all these relationships. So when you have isothermal process, there's no change in temperature. Energy as zero. When you don't have any change in volume, you have no change in heat, you end up with the internal energy being W. No change in heat, the Q is zero, so you now have internal energy equals to W. So now energy and chemical reactions, energetics. Using bond enthalpies to calculate energy changes in reaction. What you have to note is that when you're breaking chemical bonds, it requires energy. You need energy. You need to put in energy to break chemical bonds. But when bond is forming new chemical bonds releases energy. Forming releases energy. So what does that mean? Forming releases energy. It means that is exothermic. Breaking requires energy. You have to put in energy. That's endothermic. So that takes us to endothermic and exothermic processes. So exothermic processes release energy. Exothermic processes release energy, like you can see this process here. See the reactant here together, forming the product here, and energy is released. But endothermic processes, they take in energy. The reactant here, they add energy to it before. Energy is just acting like one of the reactants. It is not the reactant. You need the energy to carry out. And so this is an example. Now, looking at exothermic reactions, heat is given out in exothermic. Heat is given out, so you have the system is hotter than the environment. And so the enthalpy is negative. The enthalpy change is negative because the product, because the heat of the reactant is your enthalpy change. So when the heat of the reactant is more than that of the product, you will now have your enthalpy change as negative. So other examples of exothermic reactions are combustion and also neutralization, acid-base reaction. So endothermic takes in heat. And you see, so you have your product and you have your reactant. I say normally the enthalpy change is the reactant. So when that of the product is higher than the reactant, then you have being positive, as you seen. So we'll soon conclude this lecture. So energy changes in endothermic and exothermic processes. So in an endothermic reaction, there is more energy required. You need more energy to break the bonds than what is released. And opposite is the case in the other, in exothermic. So exothermic energy is released and more energy is released, but in endothermic, more energy absorbed. Okay, so we're going to stop this lecture here. Again, so, stop the lecture here. You can listen to it over and over again. Thank you for joining the class. I'm stopping sharing. Thank you for joining the class. So you can always listen to the lecture again, over and over again. Thank you and have a blessed week.